So hello everyone, I'm Martin Ray. I'm a Beaker Fellow at the University of Oxford. And today I want to talk to you about everything but machine learning. That's literally, if you have a distinct feeling that everything about my talk is not about machine learning, that actually is the point. Machine learning for me is what I think is the future, but it's not yet the present, and that's actually why I'm here. And today I want to get you excited about low surface brightness observation and the fact that we're going to get an enormous amount of new information at low surface brightness in observations of galaxies that I think we're going to need machine learning to properly exploit. So what I mean by this is I'm going to talk mostly about stellar halos. So here I'm showing you an extremely expensive cosmological zoom simulations where we're basically watching hierarchical structure growth. You're seeing stars being formed in all of these tiny dark matter halos. All of these dark matter halos are assembling with one another. They're all merging in this hierarchical fashion. And all of this patch here is going to eventually assemble to become a Milky Way mass object. And what you can see is that when these mergers actually happen, you see that some of these galaxies starts to get disrupted. They form these kind of streams that we heard about yesterday. And when we get larger event, like if you follow this one here, you'll see that it's going to generate a large expansion and scattering of the stars into the outskirts. So the proto-galaxies really is in the center, but you see that these mergers are generating these plumes of stars scattering into the outskirts. And this diffuse glow around the galaxy is what is the stellar halo. And it all looks great in a simulation movie like this. You can see there's a lot of information. Each of these mergers adds one of this shell and stream. But there is actually a catch. When we do this simulation, we have access to all of the stellar particle and all of the information. But in practice, these stellar halos are. So they allow us to learn about a galaxy's past mergers. I also want to point out that they encode a lot of information about star formation in all of these small dwarf galaxies that are extremely difficult to image. And again, we've heard about progress in that respect from yesterday. And finally, especially in the context of the Milky Way, they also are dynamical traces of the host dark matter. So they are great. They're really interesting. They provide us with insights into all sorts of different physics, but they are extremely challenging. And that's because they're really extended. So they're really large in terms of physical size, and they're really faint. And to kind of drive this point more clearly, I'm showing you a picture of the same galaxies we were watching the movie just before at about the depth that would be achieved by an SDSS image. And what you see is, it's nice. It's a good looking images, but you don't see all of this glow and streams and shells around the galaxy. You really have to start pushing to depths that are really difficult and tricky observationally to start seeing this elongation around the satellites start appearing, this glow around the galaxies of diffuse light. So these stellar halos are really tricky, like really, really tricky. And to again drive this point, what I want to show you is the fact that for the longest time, the only real stellar halo we knew really well around Milky Way mass galaxies was the Milky Way itself. So here I'm showing you how big is the stellar halos of a given galaxy as a function of the host mass. And basically until the 2000s or the 2010s, there was basically one point on this plot. And it's only really in the last decades that we've had a lot of progress in dedicated instruments for low surface brightness imaging. And here I'm showing you, so this is one example from the Dragonfly telescopes, and I love this picture because the Dragonfly telescope looks epic. It's this kind of giant cannon of cameras that is shooting at the sky. And the point is, to perform this low surface brightness observation, you really need dedicated instruments. They are we need different properties to the usual telescope that we're built with, and we need different reduction pipeline to the usual reduction pipeline we use for galaxies. And once we did that around 2015, we actually went from 1 to a handful, to 10 to 15 stellar halo directly imaged around Milky Way galaxies. And one of the most basic results that appear from these surveys a couple of years ago is that there is a huge amount of scatter in the amount of diffuse light that's glowing around each of these galaxies. So here I'm showing you that for a typical Milky Way mass object, we've seen, even with 15 objects, at least about a depth of scatter in the pure most basic observable, which is just the amount of light that we image in the outskirts of these galaxies. And so we kind of want to understand why, and we want to understand what kind of information can we learn from all of this scatter. Is this just purely stochastic? Is this just a reflection of different galaxies get different mergers? Or is there some information there that we can try to exploit to constrain cosmological galaxy formation? Okay, so as a quick takeaway, I want to stress that we are at about of a tipping point right now, because we are starting to image this population of extragalactic stellar halos. We are not limited to the Milky Way anymore. And this is only really going to expand, especially given LSST and Euclid. And we heard about Arrakis as well from yesterday. And to kind of showcase to you what LSST and Euclid are going to do, I'm going to repeat the exact same experiment I did from the simulated data, but this time with real observations. So this is a paper by Nacho Trujillo from the Canary Island, where he's showing the same galaxies at the SDSS depth here. And again, we can see the galaxy, a satellite, but we don't really see anything around it. Then it's done again at the Dragonfly depth, and you can see that some of these galaxies are starting to grow, that you're starting to expand the kind of dark background, and some features are starting to appear here. And when we reach this kind of landmark 30 to 31 magnitude per arcsecond square, suddenly there's a lot of features that start to appear around this galaxy. And here, the stellar halo of this one appear to be extremely asymmetric. And you can see that also we see a lot of features around this other galaxy. And this one's also massively grown, and et cetera, et cetera. And then I did a little bit of digging in preparation for this talk, and I'm sorry to be the one who puts a big quote and block of text in the middle of a slide, but this is actually taken from the Euclid preparation survey. So the Euclid preparation paper for the low surface brightness component of Euclid. So if you just focus on that number, this 30 to 31, which is about this depth of imaging, and then focus on that number here. 24,000 galaxies available for Euclid, 1 per pointing for the wide field survey. So we're going to go from a handful of galaxies, 10 to 15, that we've had, to several thousand, several tens of thousands. So we're really going to move from the single objects to the large statistical domain, allowing us to do inferences and potentially learn about galaxy formation through these low surface brightness features. Okay, so as a summary, if there's one thing you take away from the talk, is that we're really at this tipping point right now for low surface brightness observation. This is a golden opportunity to constrain cosmological galaxy formation, providing we can actually interpret this data. And this is where this talk is actually going. So this is not a statement of diminishing anybody's work. This is mostly a statement about this is really, really hard. In order to get the stellar halo right, you need to get all of these really tiny small dwarf galaxies correct, assemble them in this hierarchical fashion, get the central galaxy correct so that when a merger hits it, it scatters its stars the right way, and so on. And so it's intrinsically a cosmological process. It's intrinsically something where we need very large volumes, many objects, while also having the resolution to get many small, tiny dwarfs. And when we did that with our favorite hydrodynamical model, this is what happens. So this is a suite of zoom simulation. You run mostly with the Eagle physics. This is another suite of cosmological zoom simulations from the Auriga project. And this is from the illustrious TNG data. And so basically, when people started doing this comparison with the stellar halo samples around 2019, 2020, they quickly realized that the current cosmological simulations massively overpredict the amount of diffuse light around Milky Way mass galaxies. And on top of that, they also underpredict the scatter that one is expecting around the mean. So we are in a problem where we put too much light in the outskirts, and this was dubbed the missing outskirts problem, and it's not my choice. So if you don't like the name, I'm sorry. But it's a question of both scatter and mean. And So the problem with these types of cosmological hydrodynamical models, and it's a problem I'm guilty of because this is actually mostly what I do, is that we don't actually have a lot of control and a lot of exploration power with them. It's really hard to say, we did it, it didn't work. Why? Why didn't it work? And the problem is they are so expensive that we can't really explore very efficiently what's going wrong in the model and why we are not matching these types of data. And so today I'm going to try to kind of showcase to you that I think that augmenting empirical models is the way forward to model these types of low surface brightness data. And so here I'm showing you what we did in 2022 with Chitske, who's in the room as well, where rather than relying on hydrodynamical simulations, we use dark matter only simulations. So you still get the cosmological context, you still get all of the mergers, but from the merger tree, you use an empirical model to populate the stars. So you don't actually do any hydro or anything. And so this is actually based on the star formation histories from Ben Moster, but it's a generic idea. You could use your favorite empirical model for this. But what is really important for the stellar halo part is that we complement this by following the dynamics. We say each of these newborn populations of stars, we tag them onto specific dark matter particles. We say they are born at the bottom of the potential well. And that actually allows us to track where each star is when it's born, where it ends up at redshift 0, and to position it in the right place in the halo at redshift 0. And what you end up with, in this case, is actually a map of the stellar density, or a 3D distribution of the stellar density that is fully semi-empirical or semi-numerical, depending on how you want to see it. So this only relies on the dark matter only information, but you can see that it's capturing some of the streams here. This circle here is 20 kiloparsecs, so in the center there would be a galaxy, and all of this is basically the asymmetrical stellar halo created by the specific merger events that we're looking at for these galaxies. So this is a way to augment the traditional empirical models using the particle data information from the dark matter to also basically recreate the stellar halos in configuration space. Okay, so the next thing you can do is you can take this particle tagging technique and then apply it to a really large volume and create your really large sample of galaxies. But actually I'm going to argue to you that what I'm really interested in is, can we tell apart different astrophysical model from different mergers? There is a lot of scatter in the stellar halos. Some of it comes from having different merger histories. And I want to be able to understand how much of that scatter comes from the mergers and how much comes from my assumption about the astrophysics. And so to do this, I'm going to use a sampling trick, where rather than take another completely random initial condition, I'm going to create a new one that's almost the exact same initial condition I started with, but not quite. So if you can't tell the difference by eye, this is the point. It's almost the same galaxies. But if I show you the difference between the two, you'll see that I've actually made some changes within this black contour. And so if I show you the two movies of what this does, again, it looks very, very similar. It's got the same large-scale structure, but I've actually engineered the initial condition to introduce a targeted change to the specific merger history of this one galaxy that I'm interested in. And actually, there's these 3 mergers here around redshift 2, and if you look on the right, you might have the feeling that these 3 mergers just happened earlier. And that's exactly what I've done. I've changed the initial condition just a little bit using the genetic modification approach, and I'm happy to go into the details of how we actually achieved these changes, just to make this merger slightly earlier. And my goal is then to compare what difference does it make to the final stellar halo. And so to put this in a more quantitative way, this is the halo mass growth as a function of time. I started from the orange line here, and you can see the red line, these bumps around redshift 2, are these mergers that I made slightly earlier. And what's good about this approach is that I don't need to stop there. Everything about them is the same. You get the same early growth, the same large-scale environment, the same total mass. But I can actually take this tune and make it for a little bit earlier again, or actually crank it the other way and make this merger take go a little bit later again. And so suddenly I've scanned through these different merger histories, and I can compare the stellar halos, the resulting stellar halos in each case. So what I'm really doing is I'm introducing targeted control changes in a cosmological merger history in order to isolate how specific merger configurations shape stellar halos. And when I do that, we will immediately see huge differences. This looks like small differences here, but the stellar halos look completely and radically different. And because this is a kind of like incremental tick-by-tick approach that I'm doing, I can actually see why that is. So here I'm showing you the spherical density of stars, and you should immediately see that as I'm making this mergers go later towards the pink, there is more stellar density in the outskirts. So I'm growing the stellar halos as I'm making this merger go later. And these 5 different histories generate 1 Dex scatter in the halo mass. And again, I can go into why there is so much scatter in this, but I'm going to skip that for the sake of time, because what I really want to show to you is the coupling between merger histories and galaxy formation physics. So here, we've created these 5 histories for ourselves. They generate a lot of scatter. But what I can do is I can regenerate with my empirical model all of these histories with another set of star formation histories. So in diamond, I'm showing you the total mass, and in the cross, I'm showing you the accreted mass in the stellar halo. And I'm going to tell you that populating dwarf galaxies in small dark matter halos is a really tricky problem. We've heard some of it yesterday already. This is something I've done a lot of work around as well. So this is the stellar mass to halo mass towards the faint end here. And I'm just going to quickly show that there are really large discrepancies between different predictions for that quantity. So in blue, I'm showing you in gray, this is our fiducial model coming from the Ben Moster's star formation histories. In blue are determinations from Ethan Ladler from 2020, and in orange from Justin Reed in 2017. And the basic point is that if I take a typical dwarf galaxies around here, I can get about an order of magnitude difference in stellar mass. So there's a lot of uncertainties in the budget available, the amount of stars that should be formed and incorporated in the stellar halo to start with. And so if I retag and recreate all of these 5 merger histories with star formation histories that vary the slope of the stellar mass to halo mass relation at the faint end, this is what I get. So here we are going to shallower stellar mass to halo mass at the low mass end, and basically what you should see is that the accreted component is growing, and that makes sense. I'm building a larger halo because I'm putting more stellar mass in each of the dwarf galaxies that is infalling, so that makes a lot of sense. What was actually interesting to me is that the scatter around the mean is actually strongly reduced, and that's because this scatter here is coming from a lot of in situ stars rather than ex situ stars. And so the idea being that if you have a lot more dwarf galaxies and each of them is a lot more massive, the stellar halo building is less stochastic as a process because it's not dominated by one event that introduces a lot of noise. You're actually washing away by many different events, and the diversity in the stellar halo content actually goes down. So now, if you're unconvinced, you'd be right, because I was pretty unconvinced when we did that with this one example. And so what we did after this was to actually repeat this exact same experiment on a completely independent and different merger scenario, where we take another completely different merger history that's dominated by radial major merger at redshift 2, and which we genetically engineered to make systematically smaller and larger. And when we do that and repeated the experiment, we find the exact same thing, that the moment you start making the stellar mass to halo mass relation shallower, the diversity, the stellar halos grow accordingly, but the diversity generated by the different merger histories actually diminish. And if some of you got triggered by the idea that a galaxy of the Milky Way mass experience a redshift 2 major mergers like the Gaia sausage, this was not a random choice that we made here, and I've done a lot of work on understanding with the similar types of idea, understanding how the Milky Way can be, the history of the Milky Way can be inferred with these ideas. And so the bottom line from this, and the thing that I really want you to take away from this, is that there is a lot of information about unconstrained or poorly constrained galaxy formation physics contained in just this really simple amount of light in the outskirts of galaxies. The stellar halo mass contains a lot of information about the shape of the stellar mass to halo mass relation at the faint end. And it's not just about the overall normalization of the stellar halo mass, of the stellar halo mass. It's also about the amount of diversity that gets created through different merger histories. And so what about machine learning? So basically what I've shown you today is, at least I've convinced myself, and I hope I've convinced you, that there is a lot of information and a lot of things to be learned from these stellar outskirts. And that the simple fact that we can now generate with these augmented empirical models large banks of images from which, you know, anybody could train efficient algorithms to then infer what actually was the galaxy formation model that I used to create these images, is for me the step forward. So we're going to get thousands of images of galactic outskirts from this low surface brightness components of Euclid and LSST. They, on paper, promise us very strong constraint for galaxy formation models, but I think we are yet to build pipelines in terms of on the theoretical side and the data analysis side. We're yet to build pipelines to actually exploit this data set. And this is really what I want to trigger your brains about. So that brings me basically to my conclusion. So I haven't really discussed it very much, but I hope you got a sense that genetic modification control cosmological studies, and they allow us to establish a causal account between a galaxy's histories and its observables. By using it to scan through merger histories, we can really quickly assess and cleanly study the scatter in stellar halo content and structure, and do that at fixed stellar mass and dynamical mass, so fixing two of the big control variables of galaxy formation. By combining it with semi-empirical modeling and particle tagging, it provides us with an efficient route to assess the information content and the constraining power available in this low surface brightness observations. And finally, we are now at the point where we have efficient models that can generate large amount of data, or large amounts of simulated data, to enable the training of future algorithms to robustly infer this galaxy formation physics that we are after. And I'll leave you with my summary and take any discussion points or questions that you might have. Thank you.
So Martin, sorry. See, there was another one. You go ahead. You go, Chris.
You sure?
Yeah.
Okay. Chris Lovell. So in this semi-empirical approach, you're essentially mapping stellar populations to dark matter particles.
Correct.
And then using that to infer properties of this stellar halo.
Mm-hmm.
Are you not worried that you're implicitly ignoring processes that lead to, you know, the stripping of galaxies that are, you know, essentially baryonic processes, things like ram pressure stripping, etc., that, you know, contribute significantly to this stellar halo?
Yes.
Thanks.
Yes, there are ways around this. Okay, so there's several things to think about. So one is, because you're tagging stellar orbits to dark matter orbits are pressure supported, so there is almost no way to get a disk. So the central galaxies is almost always going to be wrong. And then you're going to have it's great for elliptical galaxies, but it's not good to make disk galaxies. Disk galaxies, because of its specific potential, will strip subhalos in a different way than if it wasn't there. And this is something that you can add to your dark matter only simulation. You can add a disk potential a posteriori to correct for that. And then there are other effects like maybe creating cores in some of these dwarf galaxies that are driven by baryonic processes that also affects their stripping. All of this is there. All of this needs to be quantified. It has been quantified to some extent, but not to the full, not to the full extent. I think the leading uncertainty right now is not there. I think the leading uncertainty is the star formation histories of the dwarf. And this is also something that has been shown in previous papers comparing hydro works versus tagging approach on the same halo, is that if you match the star formation histories of the tagging to the hydro star formation histories, you can recover the stellar halos really, really, really well. So the leading uncertainties is how much stars are you forming in the dwarfs at a given time, rather than the more dynamical effects that you have in mind. Doesn't mean it's not there. It's just it's currently subdominant.
Yeah, cool stuff. So the kind of machine learning problem you mentioned at the end sounds sort of like a simulation-based inference problem, which I'm sure people in your department have mentioned to you. So have you thought about applying the tools that, say, the cosmology community, generally the machine learning community, have developed for simulation-based inference to this problem?
Yes. I think the first step for this is to actually generate the really large sample of. So you have multiple choices. You can either sample through models quite finely to try to actually get a simulation-based inference going. You can also work at the level of the images. So take some of the images that I showed, produce really, really large banks, process them with some level of noise, and then work from that. And finally, you can use a much coarser summary statistics like the mass of interstellar halo, like I've been describing. At this point, I don't really know which one is, so none of them have been done yet. And so when I was introduced to cosmology, there was a reason we did the 2D, the 2-point correlation function before we moved to the 3 and the 4 and so on and so forth. So I don't know whether we should just skip doing all of the summary statistic and go straight from the images or from the simulations themselves, or whether the more traditional approach of going for these summary statistics is better suited. And it's something I'm very happy to discuss with the folks in the audience.
Very nice talk. Okay. So you showed a correlation between the diversity of the stellar halos and the faint end slope, right? Mm-hmm. The faint end slope that you're talking about, is that a global faint end slope, or have you also looked at halo faint end slopes and whether there's diversity in that and whether that correlates with the stellar halo?
No, in this case, it's a global faint end. So maybe I didn't explain this very well, but these are individual zoom simulations, and then I assume a global faint end slope for each of them. Okay,
so I guess a question, I mean, you think that the model framework is robust enough that if you really measured this diversity of stellar halos, that would truly tell you about the faint end slope for 10 to the 8 solar mass halos?
10 to the 8 stellar mass?
10, below 10 to the 10, let's say, halo mass.
No.
Okay.
And the reason is because the stellar halo is mostly built from dwarfs that are more massive than that. So the idea being that the slope of the stellar mass to halo mass function is sublinear, superlinear.
Right, it's mostly built by 1 to 3 objects, right?
I think it's not as much as what has been claimed before. I think, now it's a bit of a detail, but the idea being that the more massive dwarfs dominate the stellar mass budget. And so even if you add a lot of the ultra faints or the faint dwarfs or the ultra faint dwarfs, they don't necessarily contribute so much. And maybe you could pick them up through metallicity distributions and things like this. But for just a pure amount of glowing light around the galaxy, I don't think you will get strong constraint from that.
Okay, good. I agree completely.
Cool.
I don't think there's actually any information about the faint end.
The very faint end, yeah, sure.
Are you sure we can go at lunch if you want? It's not... All right. All right. So I keep forgetting to say my name, Toby Brown. I'm wondering about the IMF, particularly from the observable sides. I know it's a bit of an obvious question, but you know, you need to quantify the fraction of mass in the halo, but you don't really know the IMF of those stars, or at least I don't know a way to measure that. And you could easily see a way that that is different to the IMF of the stars in the galaxy, like the main galaxy. And then you know, this has an impact on how constraining your comparison is. But more positively, maybe you could use your models to try and get back at that issue. So I was wondering if you had a comment on that.
I think my comment was going to be your second point, which is any mass consideration always depends on the IMF. We're not at the point, the IMF in this lower mass, lower metallicity objects can be constrained indirectly or from high redshift data. But maybe the way forward is actually to map directly to the light, make the simulation go to light rather than like work at the level of either surface brightness images, surface brightness profiles, make an assumption for the model for the IMF, and then work at the level of the surface brightnesses, rather than try to infer from the observations what the mass of the halo is from the observed light. Yeah.
Okay, so let's thanks again, Martin. So we have lunch.